here, working with the ejector system here tonight. I was going to come home tonight and do a video explaining the ejector, explaining how it doesn't work. I'm having a few minor issues, but they're fun issues to have. I built this thing with the idea in mind that a few of the components weren't ideal from a theoretical standpoint, the way I interpret things, the way I think it might work, but they were a little easier to build, and I figured that I was going to find a few unusual phenomena that occur, and I have. The beautiful thing about this system here, and the level of control, the level of observation that I have through sight glasses and things of that nature, allow me to make a lot of small adjustments and make a lot of observations, get a real hands-on experience with refrigeration that you might not normally get with just a conventional vapor compression system, TXV, cap tube, all that kind of thing. Without working with this stuff for years. And I've really only been working with this for a couple of months. Refrigeration equipment, that is. I did a dehumidifier or two a few years ago. Real crude, just hacked it up, built kind of a heat pump to heat up some water in a cooler, using propane, HD5 propane. But this work here has led me to make some funny observations about the ejector system. So there's a couple things I wanted to describe that aren't working very well in this kind of two-stage ejector heat pump. One of them has to do with the flooded evaporator. I'm a big fan of flooded evaporators in theory, but actually building something that functions well is not that easy. This thing is really crude. This is one of the components that I was saying I kind of found an easier way to build it, knowing full well that I was going to have some issues with it, and I am. But I'm glad I did it because I get to observe some phenomena that I wouldn't normally see, in a conventional system, or if I built the flooded evaporator just the way that I wanted it. So I'm still glad I did it, and I got a lot of room to improve it. The other thing, of course, is the ejector. The ejector I hadn't planned on doing originally, months ago, but just thinking about it got me excited, and building a small version to test out and getting some performance out of it is a lot of fun. And then all the weird, goofy little cycles that occur, because we have two refrigeration loops in this propane system. We have the loop starting with the compressor to the condenser to the ejector to the separator column, and then back to the compressor, and then we have a loop from the separator column through a metering device into a low pressure separator column that feeds the evaporator, and then goes back to the ejector. So we have this cycle here, and then this circuit here. The ejector itself, I've had success as high as 10 psi of compression with this setup here. This is my first functioning, ejector assembly. I have a few different primary motive nozzles. I've tested 3 so far with this configuration in a few different settings, the depth that the nozzle goes down in there. And after I built the first one and tested it a few times, I built 2 more, thinking that what I needed to do was to constrict the motive nozzle a little more to get even higher velocity down through the throat, and with converting more pressure to kinetic energy, hoping I can accelerate the vapor being drawn off from the low side, and thus whenever it starts to lose speed down here in the divergent portion, that I can even gain more pressure, more compression. I'm starting to think that I kind of went the opposite direction I should have. I actually should be widening the motive nozzle a little bit because there's a limit to how much, with that amount of velocity, there's a limit to how much energy you can transfer to the suction vapor. And from what I understand, the problem comes down to shear forces. you have a vapor that's traveling much slower being drawn in, and then you have this very, very high velocity liquid being shot through the nozzle. And when there's a large difference between those two streams, you have what's called shear forces. There's just a lot of energy lost, a lot of turbulence created, and which gets converted to internal energy and intermolecular kinetic motion, intermolecular motion, which produces flash gas and increases entropy, and work is lost, and so on. So one of the things that you want to do with an ejector is you want high ejector efficiency, which is generally defined as the mass entrainment ratio. The amount of mass flowing through from the motive nozzle compared to the amount of mass being accelerated by the ejector assembly. In this case, it's the vapor from the low side. On the other hand, you also want to have high compression ratio. But just like a conventional compressor, if you increase the compression ratio from 2 to 3 to 4, in terms of absolute pressure, generally your volumetric efficiency declines and your total mass flow declines. You can't really have both. You can do things to improve both of them at the same time, but there's a theoretical limit to it. If you start increasing, given some certain set of conditions, if you start to increase the compression ratio, your mass flow rate suffers. So the total efficiency of the compressor suffers. It's very, very similar with the ejector. There's no moving parts, but you can either move a lot of mass or you can do a lot of compression. You can't really have them both. You almost have to find a happy medium, I suppose. And I don't know if I've found either one of them all that successfully. I'm actually starting to think that that orifice is too small. There's too much shear forces going on. Now I can redesign this assembly here. I intend to. This is hard brazed into this column down here. I'd like to hack it off and install a 5/8 inch compression fitting, and so I can actually change out these assemblies. The next one I want to do is going to have a more gradual angled divergent nozzle or divergent cone down here, and I also want to do another one that has a slightly longer mixing portion there. For now, I need to focus a little bit more on the motive nozzle and position of it, and try to get a handle on it. Now, I started to say before, the other issue was this flooded evaporator. I should describe the flow here soon. I don't know if conditions have changed much. Get a good view in there without the glare. Open her up a little bit. So that flow you see on the right side, that's refrigerant being fed through this needle valve from the medium pressure column. So there's a little bit of compression done by the ejector, liquid separated out, and then sent on through the metering device into the low side. But on the subject of the evaporator, if you're not familiar with the flooded evaporator, generally it's a bad thing. In a capillary tube system, TXV system, any kind of dry type evaporator, you start having liquid exiting the end of the evaporator. If you don't have sufficient size, say accumulator, you're going to have liquid slugging back to the compressor, which can be a huge problem. In the case of a flooded evaporator, it's intended to be completely flooded at all times. Most of the internal surface is wetted, and generally there's a tank of some sort that overflow liquid flows into, and that liquid can actually then go back into the evaporator. And circulation in the system is generally accomplished by natural thermosiphoning. As gases are produced and liquids carried over, liquid can then enter the bottom again and vapor get drawn away. The advantage being, if you have a common tank of some sort, you have liquid being fed in and vapor being drawn out, there's almost no pressure drop in that tank there. You're relying on thermosiphoning to occur in that system. The drawback, I want to say the other advantage here of the flooded system is the internal surface is wetted, very wetted, so high heat conductivity, and generally they have better performance than a dry type evaporator. But the problem with trying to actually build something like that is you don't have a lot of pumping flow. You can have a pump installed in large systems do, but in a small system like this, it's just not practical to actually have a refrigerant pump that's pushing fluid through there. That's normally done with the slight pressure drop in the dry type system. In this case, I'm noticing that I'm getting some pockets of gas that form and cause surging. It's regular surging that occurs. I have a lot of different ideas on how to build a flooded evaporator, an air coil type system like this, air heat exchanger. A water system would be much easier, but with a thin setup, I'm almost kind of reliant on taking existing equipment like this and modifying it. So in this case, I'm feeding liquid to the 2 lines at the bottom, and I'm essentially drawing off the 2 lines at the top. I do have one that goes up and then back down, which could be a problem, but not worrying about it too much. I'm feeding the front and the back at the same time, and then drawing off the front and the back at the same time. What's cool is that I'm getting a lot of funny cycles that occur. I'll let you kind of get a view here without the glare. You see the line on the left, it's sputtering and spitting a lot. The one on the right is just kind of feeding pretty constant liquid. At the bottom you can see overall the liquid level in the tank itself. A liquid can drain into the bottom of the coil, and then when it comes back up, it comes up that left line there. You see a good bit of liquid coming out of there. Sometimes you just see vapor, sometimes you just see liquid. But what will happen in certain conditions, it will very regularly cycle where the liquid level will almost completely drop out of sight. The amount of liquid coming out of the left line, the overflow from the evaporator, will disappear almost entirely. You just see a little bit of sputtering occur. And then all of a sudden the liquid will start coming back up to a certain height, and then not long after, that sucker will start shooting a hell of a lot of liquid out. Now what I've done is just, making observations, no calculations or anything like that. Just use a simple infrared thermometer. You wouldn't normally think this would be very good. Some aspects of refrigeration is useful, but taking the temperature on this coil here, I wouldn't normally think that would be all that useful. But in this case, pointing the infrared thermometer at near the exit point of the evaporator allowed me to watch the temperature fluctuate. Now, what the actual values aren't all that interesting or useful, but watching the values rise and fall in relation to the amount of liquid and the amount of activity coming out of the line is quite interesting, because it gives you kind of a bit of a window of what's going on inside there. Now, I know, roughly what the temperature inside these columns are based on the thermocouples that are installed, and then I can also watch the temperature of the coil. Now, I might notice that the coil temperature is maybe a few degrees above the saturation point for this pressure and the temperature that I'm reading here, especially at the bottom where the liquid enters. What can happen is if this thing gets dried out and you don't see any liquid overflowing out of that pipe at all, just like in a dry type evaporator, it can be starved, and there's only so much liquid in there, and any remaining liquid or any remaining space is occupied by just vapor and eventually a superheated gas that ends up getting drawn back and returned. Fortunately, in the case of the ejector, when it gets circulated back through, it resaturates, so the compressor never sees any superheated vapor, which is a fascinating feature of this. In the case that it's actually fully flooded, and it is for the most part here, it's actually cycling between flooded and starved, flooded and starved, flooded and starved. And in the case of a TXV, you might associate that with like hunting or something, where it's kind of hunting for the right setting, kind of superheated and then flooded and superheated and flooded, and that's what's happening here. So I observed that the temperature up here towards the top with the infrared thermometer, and at the same time, note the changes of liquid level and stuff in here. And what I find, it's really fun to watch and to observe and to try to predict, is you start to see the temperature start to rise and rise and rise and rise here. 3 or 4 degrees above saturation, a little bit of tiny little superheat, almost inconsequential to the operation of the system perhaps, and it's only towards the top. What'll happen right after that is the liquid level will start to rapidly rise here, and shortly after that, you start to see some liquid go spewing out of the top there, at which point this is becoming flooded again towards the top. It cools down rapidly, 3-4 degrees, and then the liquid level will start to drop back down, and the temperature will start to rise back up here as the gases are being superheated, and there's no more liquid there. So it's blowing itself out, really both directions. It's blowing itself out towards the top, where it's supposed to, and it's also actually backing up and blowing itself out the bottom. And so a lot of this liquid will slug back up in the tank, and then it'll slug back down mostly the drain line. It should be, because the liquid's not over, the liquid level's not generally going over top of the left line. And it's creating all kinds of vapor pockets in there, which then builds some pressure, and then the cycle starts over again. So these top coils do get wetted at times and are absorbing heat, but it's happening in a cyclic fashion. And I imagine there's all kinds of points in here with these, low swept. There's probably hardly any angle at all in these tubes, if really any at all, that these vapor pockets are being trapped in here. And this is one of the problems that I'm having with this setup of Evaporator. And like I said, it's not ideal. There's a lot of other designs I'd like to check out, but this was a really good place to start. And again, I'm glad I did it. It's really interesting to watch that cycling occur. So in terms of trying to come up with a better design for a flooded evaporator, I've considered in the past actually taking a coil like this. Well, let me first say, what I'd like to do would be to take off all these U-tubes and basically put a whole header, sort of a tank, vertically on this side, and do the same thing on this side, and then just tilt it a little bit so that vapor tends to, rise to one end and can be drawn off, and there's not so much slugging and sloshing back and forth and stuff. But as you can see, the construction of this coil, like most coils like this, consists of these single-piece U-tubes that extend the whole way through. There's no brazing joints here. It extends the whole way through to this end, where they're braced with these little connector loops. So that's really not an option. So one of the other ideas was to actually take this coil and turn it 90 degrees, so these connections are on the top, and then remove all these U-tubes, the vast majority of, really all of them, and then braze all of those joints into a horizontal tank. One thought was to, for each pair, to take one of them straight out the bottom of the tank feeding liquid, and then the other one would actually extend up a certain distance above the liquid level in the tank. So there's a general flow, but really could just terminate all of them at the bottom and allow liquid and vapor to just fight itself. It's not ideal, but I don't have a lot of other options right now. I'm not really sure what else to do. Another option, let me say this, is a bastardized version of the flooded evaporator, which is similar to, if you watch any of the early ejector videos I had, I was actually feeding from the metering device from the medium pressure tank, was feeding it right into the bottom of the coil and then out the top. So using some of that velocity to actually push things through. I don't know how well it worked. I didn't have this tank at the time, so it would tend to kind of slug back to the ejector and foul things up there. So I wanted to try thermosiphoning, and I'm glad I did. But I kind of want to avoid that. And I'm getting some success with this. I mean, the fact that I am getting a very decent amount of cooling. I don't know quantitatively how much heat that I'm moving. Just observing the amount of liquid that's flowing through there is reassuring. Something simple that I can do is just, instead of just having one in and one out, you could branch things out a little bit, have a few ins and a few outs. That would probably help matters quite a bit. And maybe another tank arrangement of some sort for some of the surging. And I'm not sure, where these vapor pockets are getting trapped. Check valve in the bottom, maybe, to prevent it from slugging and pushing back up through. I don't know, but all I know is it's a hell of a lot of fun. It's really neat. It's really, really neat. So, yeah, should have that light off so it doesn't glare so much. Anyway, so yeah, I just wanted to update a little bit I think the next thing that I'm going to do is take another one of these motive nozzles here, something like that, and drill it out or make an entirely new one. Something with a larger, significantly larger orifice, just to see what it does. Have something to compare, and you know, mess around with those a little bit. So anyway, that's just a little update for this evening, and whenever I get around to doing that, I'll do another update. Thanks for watching.